Welcome you all to the class again. So last class we learned a lot about turbulent boundary layers, and we particularly learned that uh, inside the what we call an inner turbulent boundary layer, which is also called a constant stress layer. It's called constant stress because in the limit of infinite Reynolds number, the stress inside will be constant. And I also showed you the data. I'm just replotting it here. So basically this is for the same turbulent plane co-ed flow. The straight line is the turbulent shear stress and the dotted line, red one, is the viscous shear stress, and the total stress, as you see, is not constant. It can be improved with some increased number of sampling or so. This is already sampled a lot, but it would never go to a perfect constant line. Okay, so you can see here it has some variation. Nearly, I'm not sure whether you are able to see, there is a dotted blue line here. It is not constant. It goes to constants only in the limit of Re delta tending to infinity. Okay, so we learned that about this constant stress layer, and this concept will be used in the modeling community, as well as I said experimentalists use it because you don't have to measure the near wall flow. All I can do is I can measure the turbulent shear stress here, and then that gives me the viscous shear stress on the wall. That's the idea. So I don't have to measure that part. Experimentalists will make use of that, and modeling community would say, now I don't have to use mesh closer to the wall to capture the viscous shear stress. I can just use the turbulent shear stress data to know what is the skin friction. But there will be a challenge here. We have seen from the data from the budgets of RMS. I showed you the production rate, dissipation rate, redistribution rate, all this. So what is the nature of the dissipation rate? Is it positive, negative? On a graph, right, in the budget, it always had a loss and a gain. So the dissipation rate was occurring, it was negative, right? Epsilon is always positive, and minus epsilon, when we plotted it, it is a loss to the system, right? And where is the maximum epsilon was there? Did you notice? The maximum epsilon was on the wall. Okay, if you recall the budget, the epsilon goes maximum on the wall. So viscous dissipation rate or the viscous effects are strong close to the wall. Just like viscous shear stress is maximum on the wall, and turbulent shear stress is minimal or zero on the wall, and therefore the viscous dissipation rate is also epsilon, right? It is an epsilon dependent quantity, so it goes maximum on the wall. So now if you say I don't have to measure close to the wall, I just compute turbulent shear stress and then I use this information to obtain viscous shear stress, fine. But how are you going to get dissipation rates if you don't measure close to the wall, right? So experimentalists have difficulty not getting the dissipation rate on the wall if you don't measure it. Okay, it's very difficult to measure close to the wall, as I explained in the last class, the difficulties and challenges there. So this idea is useful provided you are not interested in the dissipation rates, right? So dissipation rate is important to you. If you're looking into the budget, you need measurement close to the wall. Same thing goes with modeling community also, right? It's not just important that I compute the skin friction. If I want to know the dissipation rate in the system, then I again need to have a mesh very fine close to the wall to compute epsilon. So one must go near the wall. We cannot ignore it. That's the point. Okay. So constant stress layer, fine. The idea is interesting and we can use it in the modeling, but you have to be careful that near wall is also an important place. Viscous effects are dominant there. Okay, fine. So now we move to, so in the last class, or to summarize, what we learned is we have an inner turbulent boundary layer, which we also call it as constant stress layer. In constant stress layer, further we have three primary layers. There are other layers. For this course, we will not go into details of that, but we have seen that there are primarily three sub layers here. Okay, three sub layers, which is you have a linear sublayer, and from data we know that here your u plus is y plus. So that is your velocity so close to the wall is just nothing but your wall normal coordinate. Okay, it just linearly, as you go above the wall, the velocity just goes linearly, linear distribution, very close to it. And then you have a buffer layer. This buffer layer is very important because most of the turbulence generation rate occurs in this zone, and this is the zone where we have seen that there is a equal computation between turbulent shear stress and viscous shear stress. They were both becoming 0.5 in the previous graph, right? If you just go back to that graph and recollect, you can see here it's reaching about 0.5 here. Both are becoming equally dominant in this zone. And then we have an inertial sublayer. Inertial sublayer. This inertial sublayer, we didn't discuss much about it, and I said that this is also an overlap zone where your outer layer and inner layer equations are both valid here, and inertial sublayer is also called a log law region. Basically, if you want to represent your velocity as a logarithmic of y plus, that is the idea. And in the data we see for some flows it behaves like this, and there is, of course, somebody wants to represent it as a power law of y plus, linear here in the linear sublayer. In the inertial sublayer you want to do it in a logarithmic fashion. Okay, so it looks like this. If you want to write it down what a log law looks like, u plus is 1 by, this is kappa, logarithmic of y plus a constant b. Okay, so here there are two constants here, it is this kappa and b, so I can write it here, kappa and b here. So you are essentially representing again your velocity in the inertial sublayer as y plus. So it's an empirical relation, so you can take the data and fit and see. So this knowledge has not come from theory. Both u plus is y plus and there is a logarithmic zone. This is coming from the data. You take many data from many turbulent boundary layers, from pipe flow, channel flow, boundary layers, wherever you have a smooth surface, a flat plate boundary layer, you take data and then you fit, and then you see that you get an empirical relation, and then they see that this constant now here or the kappa here, okay, kappa is the von Karman constant. Which is usually you see the value as 0.41, sometimes it is 0.40 also, but it's 0.41 is commonly used, and the other constant b, this value you will see it as 5.2. Now logarithmic law or this so called log law, people say it is universal, but sometimes you do see this value changing to 5.5 also or 5.3 and so on. That is to see that whether it is fitting to their data. Okay, so Yeah, so the data is like, as I said, it's an empirical correlation, and if you happen to have a flow where your data fits for this, it's fine. Otherwise, it's not a problem. Okay, you don't have to worry so much about it. And somebody asked a question, a good question, that whatever we have discussed, this 3 layers or the other layers, is it all going to be there all the time in all types of turbulent flows? No, right? As I mentioned, turbulent flows are different types of flows. Each flow is different, and even in a turbulent boundary layer, the boundary conditions that we have applied is important. Now we have taken a smooth wall. If you take a rough wall, okay, and depending on the roughness height, many of these layers do not exist, they vanish. So usually in a rough boundary layer, what happens is something called a roughness sublayer comes in, replacing this inertial and buffer layers. Sorry, replacing the linear and the buffer layer. So depending on the height of the roughness, its influence changes. Okay, and so I will not go into a rough turbulent boundary layer, but you just need to know that as long as your surface is smooth, whether it is a pipe or a channel flow or a boundary layer, this formula should work. Okay, so this is this formula here, call it equation 1. This is for same for a boundary layer or a pipe flow or a channel flow. Different types of internal flows or semi-confined boundary layers. Okay, is this clear? I think with this we can move to the next chapter, RANS modeling, chapter 4, right? RANS models. So now we are going back to the Reynolds average Navier-Stokes equation, the first governing equation that we derived, and we see what will happen to when we try to model here. But if you recollect, I said there are primarily 2 classes of turbulent models. One is called eddy resolved models. That means you are trying to capture some of the turbulent phenomena and then model some of the turbulence. So some turbulence is captured and some is modeled. But when it comes to a RANS model, this is a statistical approach. So this is a statistical approach. So the entire turbulence in your flow system is modeled here. Okay, nothing is actually being captured. So every turbulent eddy that you can think of is modeled in a statistical approach. Okay, and here first class of models that we consider is eddy viscosity models. Okay. Eddy viscosity models. So let's write the RANS equation to see what we learned from there. So we have, if you recall the RANS equation, you have the right hand side terms, pressure gradient term, and then I will write the 2 stress terms together. So I have viscous part and the turbulent part. Let's call this equation 1 here. So now we know that this is the 6 extra unknowns. That needs to be modeled to close the equation, otherwise the equation is not closed, right? So we proceed with this idea of this eddy viscosity here, and the idea stems from essentially like very similar to the Newton, the Newtonian idea, that is the Newton's law of viscosity. that it's a combination of two things. First thing is that now I can write this as a sum of two different stresses, a turbulent shear stress, or let's say a turbulent stress and a viscous stress. And then we just saw that in flows, in some of the turbulent flows, this eddy viscosity model is not made only for a turbulent boundary layer. It is being used for all types of turbulent flows. But if you just focus on a turbulent boundary layer, we just learned that there is something called total stress and a constant stress, right? So that kind of an idea can be used here to model. So this is your total stress, right? And in the, according to this, just like the analogous to Newtonian closure of your momentum equation, they used a molecular viscosity or a kinematic viscosity component here. So the idea is here now, if I rewrite this using what is called an eddy viscosity, okay. So the equation would be, I have the left hand side a pressure term plus the dou by dou xj. I would like to write this as nu plus nu t dou ui bar by dou xj. Now this is the exact equation, okay. This is exact equation. No modeling is done, but here when we are moving to here, this is already a modeled equation. And here the idea of this total stress is being used to think it of like a lumping together, and this particular is also called a mu effective viscosity. So when you write codes, or in many commercial codes, they use this concept of an effective viscosity or a effective eddy effective viscosity, I would say. So here mu t is what is called, mu t is the eddy or turbulent viscosity. You should remember that this mu t neither represents viscosity, neither represents any eddy, okay. It's just the name has come. You can definitely call it turbulent term because this nu is representing the molecular viscosity effects. This nu t is actually being used to represent the Reynold stresses or the turbulence stresses, and therefore I would agree that that's why the name T is here, mu T. So it's a turbulent component, yes, but physically it's not anything to do with viscous effects, or it doesn't represent or capture any of the eddies, okay. You are completely taking a nonlinear effect here. This has u prime, v prime, v prime, w prime, w prime. So this nonlinear nature of turbulent behavior is completely replaced by your strain rate and a scalar quantity. So this is also your, the moment you made it a scalar, obviously you lose the directional dependence. The anisotropic nature of turbulence is actually taking a loss here by modeling it as a scalar eddy viscosity, okay. But the idea is, as I said, very similar to your analogous to the Newtonian closure. So this modeling idea is analogous to Newtonian closure. That is relating the stress to strain rates, and therefore you have minus ui prime uj prime, the Reynold stresses that you relate it to nu t dou ui bar by dou xj, the strain rate. But then this is not the general expression that you have. Nu t is said, okay, it's a, we want dimensionally it should have same value, it should be meter square per second, because there must be dimensional consistency between nu and nu t when it is modeled like this. So it will have the same dimensions as a viscosity, but its effect is not like a viscosity here. So, but this is not the general expression what we are doing it here. So general expression is actually coming from what we call a Boussinesq approximation. Okay. Boussinesq approximation. Which gives you a general expression for this Reynold stresses. Okay, generic closure for the Reynolds stress term, which is minus ui prime uj prime over bar. This is now being closed using a model. So this is now set equal to 2 nu t Sij over bar, that is the mean strain rate, minus 2/3 K delta Ij. Okay, so if I take this, so this is your Boussinesq approximation. Now I have 6 unknowns here, modeled as 2 unknowns, nu t comma k. Two unknowns has come here. So the equation is still not closed for you to work with, but at least the 6 unknowns which represents the anisotropic nature is moved to 2 scalar quantities. Okay, this is a tensor here, so this had anisotropic nature. This is moved, now this has become scalar. K is the turbulence kinetic energy here. Okay, so K is turbulence kinetic energy. Now if I just started this course with chapter 4, obviously you would not know what these things are. You would not know what is a Reynold stress, you would not know what is turbulence kinetic energy, right? Now the theory chapter 2 will help you reconnect with all these terms, but of course all those equations are not closed. So we go and close these equations with some arguments that we are going to make. Right. So yes, so this is the expression that we have. Now the question comes is, of course, if I now little bit expand this equation, let's call this equation 2 here. So equation 2 is going to be substituted in equation 1 to close equation 1, right? So you have this viscous stress part, and then this turbulence stress is replaced by the strain rate. So that goes into that part. So I have now, if I expand it, I get minus ui prime uj prime over bar is equal to, I get essentially 2 nu t dou ui bar. I am expanding the mean strain rate tensor, dou xj plus dou uj bar by dou xi minus 2/3 K delta Ij. Obviously this goes away. When you substitute this Reynold stresses inside your equation here in equation 1, okay, so and then apply the incompressibility, another term will also vanish. So this is dou ui bar by dou xj survives, but there is also dou uj bar by dou xi. So dou by dou xj divergence of dou uj bar by dou xi, that term will vanish, and then it will recover to this. So this is the final equation that is coming in here, that will drop out. But the generic expression is here. So this is your equation. Now the question is, stress is being related to the strain rate. As I said, this is your stress and this is the strain. But then what is this? Why is this term coming into picture? So the question we are asking is, why this minus 2/3 k delta ij has come? Why 2/3 k and why k? You can model this by any other term. Why are we introducing this particular idea here? So question you have to ask is, why 2/3 k and why k itself? So we will see why this has been introduced. So this is not arbitrary, there is some thought process in this.